Good day to you all. Here is the second section of the Handson number 2 on evaluation of electrical properties of materials using density functional theory. And in this part, we are going to be looking at how to do the density of state calculation. So, as we've explained in the class, that the density of state tells us about the energy levels that are available, or the number of states that are available in a material. That is the energy levels available within the crystals. So we can have the s orbital, the p orbital, the d orbital, and how far does these orbitals contribute to around the Fermi level of the materials. So it's an important aspect in analyzing some properties or some applications that a material can be useful for and how that material can be tuned. So now we go straight to the hands-on, which is we go straight to calculating the optical properties. So the last time we went on to talk about optimizing our system, that is doing an SCF calculation, then relaxing the system, then doing a VC relax calculation to obtain our optimized lattice parameter, and then running a converged another SCF with the already converged files that we have. So here we are going to start from there. Now we have a well converged system. Our SCF file here now is converged using the converged lattice parameter, and we use our converged key points that we've already optimized to be 666, and then our cutoff has been we've optimized our cutoff to be 40. And then we said since our cutoff is now 40, we need to increase this from 100 to 200. Why? Because it was 25 before, so it was now, then they did it times 5. At least it should be, the charge cutoff density should be 4 times the 4 times greater than the cutoff energy. So now that we have 40, we can start from 160, or we can use 200, and by default some people said it should be times 8. For plane wave, if you are using PAW pseudo potentials, that it should be times 8. Some specify times 12, times 10. So at least the minimum is it should be at least 4 times greater than your than your cutoff energy. So now we are going to run this converged SCF file, which is optimized, our optimized SCF file. So we navigate as usual through the Ubuntu terminal. And as we've said earlier, we need to take note of this. If you are using Linux on Windows and you open your Ubuntu terminal, you need to first do this. But for those of us using Linux directly, you don't need to do this command that I did first, because you can read the folder direct. It is Ubuntu terminal working on Ubuntu. But for Ubuntu terminal working on Windows, we need this. So we can access all our folder. And this one of the what we should draw our attention to while naming our folders. Let me go here. So if you name your folder with a space, if there is any folder you name with space, it is very challenging for you to type this in Ubuntu and you think it's going to go to the folder. It will not go, because Ubuntu is not that compatible with naming folders with space. So what mostly should be done is, if I want to correct this, though you can do it, it is going to open it for you with some slash. Once I type MSC now, it's going to open it for you with this 2 slash. It's going to put a slash between them. So but the proper name, the proper way to name is The proper way to name a folder on Ubuntu for it to be readable, or I think in um, in terms of programming, is to name it with underscore. We should use underscore in naming, and it's more compatible for the system to read underscore. So let me go back. If you want to go back, you press CD, then to slash, and this you go back to the previous folder you had. So let me re-enter now. We can see it goes directly. If I go back again and tell the system CD MSE, and I told it to complete it for me, you see it doesn't put the slash that it has to put here. So that is a conventional way for naming folders that is mostly compatible and readable for Ubuntu. So let's go. Then we open our folder CD, I think Silicon DB. Okay. I think I have this. So now we have all the folders in DOS. So now let's run our command with pw.x. And one thing with the Ubuntu terminal is it stores your previous command. If provided they are not long, you use them. It stores it. If you've not done many commands, you can quickly recall all what you have and then you run it. So this is it. You can recall your previous commands, but I think pw.lex have been run. I use pw.x for expression. So silicon dot scf1 dot in, and I can see I want my artifact to silicon dot scf dot out. Let's do this. So it's running. Then we have a file here that will be created, silicon.scf.out. Here is it. So apart from the total energy, this is another information we can obtain the from the input file of our output file of our quantum express, or the Fermi energy level. So I think we can move forward to now run an NSCF calculation, a non-self-consistent field calculation. Here we have, this is just what you have to do. The SCF section, you just have to edit it to NSCF. Then you should, we talk about adding an output directory because you need some folders to refer back to for NSCF calculation. Some of the charge density stored in the SCF is required to run the NSCF calculation. So we need to always create an output directory folder, which is this .tmp, because if you are not creating it, it will keep on storing those charges in your folder you are running, and then it will be too, this folder will look tattered. You will not be able to sort out what you are doing accurately. So, and this folder output directory should match with what you are currently doing. It should match with the folder of the SCF. So here we are. This is the name TMP. You can name it anything. You can name it bin, bin. You can name it dustbin. You can name it folder. Just name it anything. But mostly it is more people name it TMP because it means temporary folder. And if you go to the quantum expression documentation, you see people talking. You see they are talking about a temporary folder. Even if you go to websites talking about espresso files, they will tell you the temporary folder. So because it's more convention to call it creating a temporary folder, so people used to use the short form TMP, but you can name this section the output directory anything you want. But what should be is that of the SCF should also match with that of the NSCF. So now we said we are going to include two sections in this calculation. So notice the IBRAV here. We said we are using FCC, and then IBRAV for FCC is 2, and actually this is 2. It is not like the first answer that you are using an FCC structure, and then your IBRAV remains was used as 1. This is the proper IBRAV for FCC because what? It's a primitive cell that we are using. So the IBRAV, the correct IBRAV will be 2 for the primitive cell for FCC. So now we need to include what end band in addition to what we have in the SCF. How do we create this? You copy your file in the SCF, then you put NSCF, but sometimes Burai will generate something like this for you with the expressor.those. You see it expressor.those.in. It will generate. You just need to edit to suit your own parameters. So you had the end-band section, which we said you can get from your output file of the SCF file. And that is why your SCF file, we said it should be converged. You should make it, optimize it, because what? You need this number of Consham state, which is 8, and it's what we call the end-band. So if your SCF is not accurate, it means you start missing the accuracy from the NSCF calculation. So now, so after adding the handband, which you get from your SCF section of number of Consham state, so you keep here smearing. We are going to do something about this later. But now, for now, you keep it smearing for at least metal and semiconductors. You should keep it smearing. Then then you have to what? Increase the K point mesh to at least times threefold of what you have in your SCF. It should be a more denser K mesh for the NSCF calculation. So at least since we have 666, we can use 18, 18, 18. You can use 24, 24, 24. But if anytime you are doing continuous pressure calculation, you optimize your as you're optimizing your calculation, you should also optimize the usage of the computational core hours. If 18 is okay, it's giving us the real proper description of the material, we don't see any reason we should increase the fold of what we have. So now this is just the section. To recap, what we will add to the NSCF section is 1. Changes from SCF to NSCF. 2. Make sure that your output directory is matching with that of the SCL file. Add the number of Consham states, which you can get from your SCF file to this, which is the number of band, and in the SCF output file you get it as the number of Consham state. Then here, make sure you keep this to be smearing for metals and semiconductor. At least it should be smearing. Then here you have to what? Increase your K points to what? To be more denser by threefold or by fourfold. So now let's try to run this and see what we can get. You can see the calculation is taking time more than our SCF calculation. So that is why you need to optimize the K point to be something that is reasonable. You should not use by sixfold like 36, 36, 36 for the k point, because we say you should make it more denser, but you have to think of the computational hours also, the computational resources that you are using. Okay, the calculation is done. So this is the folder. Yeah, it's done. So you don't have much file to extract from here because it's just a recap of your SCF file that you did. So, but the charge density have been stored in. So you see, it has been stored in the temporary folder. You see here it is saying the Fermi energy now for the NSCF is 8.81837 compared to the 8.0612 we have in SCF. It told us there's a little bit of discrepancy, but that is not much. They are still very close. So now the charge densities have been stored, the density of state have been stored to the temporary file. How do we extract it to be what we can plot? So you need to prepare the DOS file. This is now the file that will calculate your density of state for you. So here you have to say this is for projected density of state. So here we have. So you define this section, those instead of calculation for SCF file. So here you define this section as those, and then output directory should match with your SCF and NSCF. Then your file those means what should be the name of the output file Quantum Espresso is going to extract. So I name it silicon dot one dot that. But if I, because I have done one before, let me name it silicon dot two dot that. Then the Gauss is our more of related to the charge density, and then we have our delta E, which is the step to which you will be moving between your what, the minimum energy you want to calculate, which is minus 50. This is the minimum energy level, and then this is the maximum energy level of 50. So your file should be like this. So you can run this. So in this is where you don't use pw.x, you use a post processing command of dos.x. So you call your file. So it's told me error. So this is good. So let's figure out what error it is. These are something that we will always encounter in Quantum Espresso. So our ability to read them is what defines our expertise we have in Quantum Espresso. So it says reading those name list, fatal error, input file silicon dose not found. So it means there is no silicon dose dot dose that can run with what NSCF with the DOS command. The DOS command cannot use the folder that I named with silicon.dos because it's for NSCFI, and there is no any file named silicon.dos. So now we need to figure out what can we do to correct this. Yes, because I didn't add .n to it, so it cannot read the file, it cannot access the file. So the error is in naming the file. So this is what you need, the skills you need to develop while using density functional theory, your ability to interpret the error messages you will be getting. So it means we need to add .in And here we go. Yeah, we have our output file now. The crash message has gone, so we can open our output file and see silicon does those dot out. Yeah, we get this. So we can still see this file. There is nothing readable that we need. So where actually is our file we want to read? We name it silicon those.2.dat, right? So our extension for naming the those plottable files should be .dat. You can say it's that here, so it will be the extension should be .dat. So this is for one. So the one we calculated is 2. So this is it. Here we are. We get it. This is readable. So now we have many ways to plot. This is our energy levels from -50 to this is from -50 to 50 as you specified, and we specified a step of I think 0.1, right? So this is it. It does what we ask it to do. So, and this is the Fermi level. It gives us the Fermi level. This is our integrated density of state. So here we'll be plotting the density of state. Integrated density of state, you can plot it also, but we will be focusing on plotting the density of state. If you need your application need to plot density of state, it's still easy to combine it with plotting the dot. So here we'll be plotting the dot with any plottable file, any plottable software you have. So I think let's try to use the basics one people use that everyone can install. You can install xmgrace using the command sudo apt and get install grace, I think. So you can install xmgrace, then you click here, it asks for your password. So what Grace is already the newest version, so I have the newest version, but I just did this for some of us who don't have Grace. You can also install new plot. You do the same thing, sudo apt get install new plot. It will install new plot for you. So these are the two basic software that you can use from the terminal to plot your output file without doing any extra job. So now let's use Grace. I just call it xm Grace, then the name of my output file silicon does those silicon those two that, but you should make sure you are in the folder where you have that your file you want to plot. Silicon does two that should be, you should be in the folder. If you call it in another folder, it will tell you it cannot find that file you told it to plot. So let's grace, this is xm grace. Now we plot it with xm grace. So you need to do editing with xm grace. So if you are familiar with xm grace environment, good, you can use it to plot. So there are tutorials online that show that you can learn how to plot with Grace. But for me, I don't mostly use Grace to plot. You can use new plot too. I think if I have new plot, just click on new plot. Then you type command. So their previous command, it also store our previous command if you, in case you forget the command to use. So you just tell it plot. So I'll call my input file name silicon those two that dot, I think, yeah, you don't need dot new here. You should be able to plot. And here you use those that are familiar with MATLAB or Python. This is something that MATLAB and Python 2 does. You can specify the line type, the line width, and at what ratio it should be. X should be 1:2. So here we are. So we get it. So here we can adjust. You see, we specify from -50 to 50. But you can see that most of the where the density become pronounced, there is no contribution from around -50 to up to something of around -8 or -10. There is no much contribution. From -8, the contribution majorly comes from around maybe -8 to around, let's say, maybe 18 electron volts. So all these extra energy levels that we added to include are not what meaningful. So what you can do, you can adjust it if you are familiar with using new plot commands. So I think you can, let's see if I have previous command. So for those of us that are familiar with, I think let me try this set X range. So I think I am not much that familiar with the command again. So some of us that can recall the command, you can use it. Yes. Okay. Yeah. Set X range. So let's see our plot. It does not reflect. Okay, you use replot. Okay. Yeah. Here we are. So you can see it has deleted some levels that we don't want. You can still readjust it. You see the contribution from -20 to almost around -6. 6 is still not pronounced. So let's still maybe adjust our X range. So here we are. So you can see this is where the meaningful contribution comes from. So these are some of the ways if you want to use new plot or an XM grace. The only advantage they have is you can plot it from the spot. You can plot it from the terminal. Then you use commands. They are scripts you use to run new plot. So, but mostly it's more convenient to use an origin if you have access to origin. So let's just click this Control A, and then I think sometimes, okay, let's try putting it into, but sometimes too, Origin might not accept the format. You need to first put it to Excel to moderate it. Okay. So I think for the DOS, it will accept the format. It is the partial density of state that Origin cannot read the format. So let's put it in Origin and plot. So just Control V. So we need to adjust our E in electron volt. And let's say DOS, we have E. Then here is our integrated density of state, which, so let me save the family level here so we can be safe if we want to recall our family level. delete this. So let's delete this. Yeah, we are saved now. So let's plot and see what we have. First, let us plot the density of states. Okay, the unit for this is electrons per electrons per electron volt. Good. So you can manipulate the axis and do the editing of what you want to do. It's minus 20 to 20. And then let's keep this from maybe minus 0.1 to maybe 1.6. Apply. Good. Okay. So we still have something to do. So here we have the Fermi level. Here our Fermi level, let's note what is happening in the graph. Our Fermi level is not at 0. Okay. So our Fermi level, it told us that our Fermi level is 8.1846. So it's around here. We've not shifted our Fermi level to 0. This is not the Fermi level. This is still the valence band, and this is the what conduction band. So what can we do is, if we want to shift our Fermi level to 0, you have to subtract the value of the Fermi level from your energy levels. So what we say here is, you write something like your column, this is column A, minus the Fermi level. You subtract the Fermi level, energy level from it. We are good to go. So let's see how our graph will be shifted. Here we are. So we can now adjust this graph to obtain something that is more wider. That was why I kept it minus 20 very wide, because if we subtract the Fermi level, we are going to have some shifts. So now I think we can start plotting from maybe around minus 16 or minus 15 to something around, let's say, 15. So you can see our graph is a little bit open. And okay, and then you can do the rest. I know. So yeah, if you have subtract the Fermi level, you need to indicate in the publication when you are publishing that you have subtract the Fermi level by changing this to E minus EF in electron volts. So this is the what this place will be, and this one is valid density of state. It is. So some people used to name it fully density of state in electrons per electron volt. Then you finish up the graph. Okay. So the next thing I can do is, if I want to indicate where is my Fermi level now, our Fermi level is approximately around 0. So I think the Fermi level given to us by the SCF is more appropriate, because if we have used 8.0684, our Fermi level will have been shifted to exactly 0. So let's you can indicate your family level, which it's very important in when you are when you are plotting it. So I think you can indicate date, show, thickness, maybe let's say one. Okay, you come here, I think it should be, are we adding vertical? Let me see. No, we are adding horizontal. Let's call it one. Close it. Apply. Wow. No. Okay. Now. Yeah. So this is the family level we actually want to apply. Okay, yes. Okay. Apply. So this is where we want to use to indicate our family level. So the family level shown by the SCF was more appropriate. So you can adjust it because you can see this one does not fall at the around the family level exactly. So if you have used 08.0684, maybe we will have it exactly at this point. So now here you can see this is our what? Valence band, and here is our what? Conduction band. So here is how you can make a plot of density of state. So we still have the partial density of state. If we still have time, let's quickly go through it. So if you want to plot the partial density of state, what you just need to add is you had this, you prepare a file similar to what you use to plot the dots, but here you use proj wfc proj wfc similar to what you did in the doors, but here you have to use file pdos. You should not, you should remember this is file pdos. If you use file dos, you keep on running and running, it will never create the output file, you keep on receiving error. So it should be file pdos, and I think the extension is .pdat because sometimes I used to get error. So if I use .dat directly, but sometimes if you use it, you see it works, but sometimes it will ask you to use .pdat. So you need to just try to change if you receive error, maybe from .dat to maybe pdat. So now let's run for the projected density of state. So your command will be, now you use proj.x, I think, in, then you call the name of your input file, silicon, dot those one, maybe dot in, and silicon dot those. So I can name it what I want to, anytime I want to name it. So let me name it maybe 3, so we don't confuse what we have. Our file is what we have before. So command proj notify. So at least let me quickly glance through. We have an error, yes. So yeah, it's projbwfc.x. Okay, it's running. Here is it. Now, okay, we name it. This is our dot. Let's check what extension did we call the dot file. It's sid.pdat. So let's see. So here is it. So here our pdos output file. So silicon has the s and what p orbital only. That is what we have in silicon. We don't have the d orbital. There is no f orbital present. We only have the s and p orbital present. So for you to plot the pdos, you need to do some work. So this total density of state plot you have in this file, this one, if you plot this, is still the same as your what? As the dose file that we plot. But you see it has eliminated from minus 50 to 50 because this is actually what we have from minus 5. If you watch when we were plotting, the contribution majorly start from minus 5 from the negative to around maybe 16 or something in the 20, yeah, in the positive side. So this P dot total will give you the actual densities, not like the density of state that will give you even the energy levels you don't want. The P dot, this summary file, will give you the exact densities you have. But when you edit the density of state and you do this, still they are the same plot. So now how do you plot this s orbital and p orbital to see their contribution? So this is where you have to make an Excel file sheet. So I will just try to do extract one and then you can do the remaining. So what you do is, this is the integrated density of state and this is PDOS. So from our s orbital, the integrated density of state is still the what? The PDOS, the partial density of state. So if you extract this, you do Control A. So here is it, I have it here, but let me just do an example by opening a new sheet. So I will paste it in an Excel sheet because um, if you copy it in origin direct, sometimes it's not able to separate it into columns. So you need to separate into columns. Yeah, finish. So we have our columns here. So here we have. So I can delete this integrated density of state or PDOS. Anyone, they are the same thing if you watch the value. This is for s orbital. For s orbital, it's always normal to have what? Your integrated density of state in the s orbital is still the partial density of state in the s orbital. So I can delete anyone I like. Let me delete, but if I don't want to confuse with the name of file, I can say this is what? Silicon S1, S orbital 1. Why did I name it 1? Let's go back to our folder. I have what? Contribution from the what? Subhanallah. I couldn't find the first one again. Okay, here is it. Oh, I don't know how comes I rename it to this. But this was the first one we extracted now. Yeah. So you see we have two contribution from what? S orbital. This is S orbital. This is another S orbital. So you extract this the same way we do it. You do it here. You do control. And if you watch again, your integrated density of state is still matching with your what? With um your partial density of state. So you do the same thing. you do the same thing like this, and then you have also obtain something like this: silicon 1s, 2s. Then the contribution of the s orbital is the addition of these two. This one, this s, this first s and second s contribution, you add it here, you get something like this. Then you come to the p orbital and do the same thing. We have the first contribution from the p orbital, so you do the same thing. So yeah, what you just have to notice, you can see you have what? Integrated density. You have here your p dots. Again, you have three p dots here, because we know this p orbital will split into three when it enters into the magnetic field, right? We have for the angular momentum of the p orbital, it is what? It has -1, 0, and 1. And this is actually what we are seeing in what? In our what? In our partial density of state. But the integrated density of state is the summation of these three. You can see they are matching each other. So the integrated density of state is basically their what? The summation. So let's just do something like this and test actually if it is the same. So I will just multiply here by 3. 2, 2, 3. So we have 3.51 exponential of -9, which if you look at the file, this is actually 0.3582 or 3.51. Close, they are the same, so you can see it here. So what you do in this case is, when you extract it to your Excel file, just delete the remaining PDOs. Delete all the PDOs. When you extract it to Excel file and you change it to column, so delete all these PDOs and leave the integrated density of states to be your what? 1p, then this to be your 2p, and then you sum them. 1p plus 2p will give you the p orbital contribution, and these are the folders. So what will you copy to origin? You just need this section, the s orbital contribution, the p orbital contribution. This is what you are going to copy to what? Origin. Or maybe you copy all of them, because it does not allow me to copy some section. I will copy all of them, and then just delete the section we don't want. We don't need this. We don't need this. We need we don't need this. And again, we don't need this. And you can see, you can just plot them. See. Basically, it's just the same process we did. You have to use your formula here to subtract your Fermi energy. This is the same value. You change it here to E minus AF if you subtract your Fermi level. And what is the orbit the unit here? It is still electrons per volt, just like what we did in the SCF. And then you can plot, and you see we start having the contribution now. It is vivid. We have what? So these are our what? Contribution. So the s orbital is red, the p orbital is the s orbital is black, and the p orbital is black, is the red. So you can see the p orbital is contributing more. But the best thing is for you to plot this with your what? With your total density of state here. There's a folder that comes along with it here. This folder that has this .p .dat. So this one, this final one that has the total density of state here, just copy it. You can see this is the density of state. This is the p does, the total p does. So you should copy, you should plot it along with the what? With the total density of state, like think I have it in this. Yeah, yeah. So you can see I have the energy level subtracting the Fermi level. I have the p dot section, electrons per electron volt. So you need to also copy this out. This section here, you need to copy this total p dose. You need to copy it out, which is actually we call it the partial density of state, but still is still the overall density of state. Then this is the contribution of the s orbital that we just extract now and plot. This is the contribution of the p orbital. So what did we add to what I just showed from the previous origin? Was we had the total density of state, the actual density of state. This plot here, we had it onto the graph so we can be able to compare. If you plot the s and p contribution only, you cannot compare it to your reference, which is the total density of state. How much are they contributing? So what do we see here now? We have the s orbital, which is red, our p orbital, which is green. There we are going to say that one. Then the silicon p orbital is the one contributing more to the what? To the density, the electron density or the electronic state of what? Silicon. So if you want to tune silicon, it's most likely you are going to tune the what? The p orbital. If you can work on tuning the p orbital, then it means we can be able to what? To tune silicon properties more. We have the higher chance of tuning the p orbitals than what? Tuning the what? The s orbital. Because if you tune the p orbital, you can be able to change more properly because it is the what that contributes most to the what? To the density of silicon around the Fermi level. Also, you can see it has the highest contribution around the Fermi level. And this is how you can plot what? Density of state and the partial density of state for applications or calculations that require you to plot them. And we are going to stop here and leave the band gap for another section. Another session. Thank you.